Okay, so welcome to lecture number 38. Yeah, so I just forgot to send an email. I'll be sending soon after the class, but anyway, nevertheless, I'll just announce it here so that it's on record. So, so based on lots of email responses that I had for forwarding this request for starting the exam tomorrow. Okay, so lots of people have mentioned several constraints. Okay, so constraints on 4th. I think many of you have some assignment submission on 4th. And some of you having some activity on 3rd. So some of you preferred exam from 4th to 7th and so on. Okay, so what I'll be doing is, so this time, so we'll just change the plan slightly. So we'll have exam. So sorry, it should be quiz. Quiz 2. It will be available on the morning of 3rd November around 9 a.m. to 7th November. Okay. But once you open the quiz, so 72 hours for answering. You should answer within 72 hours. Of course, only one attempt will be allowed. That is, once open, answer should be submitted within 72 hours. Okay, so that is something crucial difference everybody should note, because earlier we didn't have that, so that everybody gets exactly 72 hours. Okay, so this should be giving you enough window. So like quiz one also effectively open for 5 days, I think. So this will also be effectively open for almost 5 days. And you can take any 72-hour window suitable for you and answer the question paper. Okay. Yeah. So again, the model will be the same. It will be a random question paper. Yeah. So this time the pattern will be there will be just 3 questions out of 30. Okay. So you can expect one to be writing an algorithm and probably proving correctness or proving properties of the structures that we have seen, either shortest paths or minimum spanning trees. The other 2 will be running some algorithm on an example. Okay. So yeah. And syllabus, like I had announced in my previous mail, whatever we covered after quiz 1 till lecture number 36. That is, I think 36 would be Monday. Okay. Yeah.
So Session has a doubt.
Okay. Can you read it out?
Yes, sir. We can still submit any number of times within 72 hours, right? Or will it get locked
No.
down after
No.
a...
No. Only one attempt. Only one attempt. If you submit, it's it.
Okay, sir.
Yeah. So I don't know how. I mean, what do you mean by submission? See, once you say you are done with the attempt, that's it. Okay. So you cannot have the second attempt. When I say second attempt, the second question paper. So I don't know
No, sir.
how the.
Actually, oh,
Yeah.
okay. Actually, what happens is in assignments,
Uh-huh.
when usually students submit, actually they can submit multiple times, and the last version will be taken for evaluation that was submitted before the deadline.
That is probably how it happens even now, I think. Okay, I can see, okay, submitted at this time, submitted at this time,
Yeah. If you
but
choose to resubmit again, then it will be like replaced by the last submitted one if it is
yeah,
before the deadline.
yeah, that is how it happens even now, I think. It's by default, it is like that. Okay, but see, I think there is also something you okay, so probably resubmission. Okay, I'm not very sure. Okay, so if that is happening in previous exams, it's the same thing here. Only thing is you'll be given only 72 hours. So was it being allowed in the previous exams, quiz 2 and assignment? I'm sorry, quiz 1 and assignment 1 too?
I think irrespective of the deadline, what I feel like, irrespective of the deadline, if you once you submit or finish the submission, you are not allowed to resubmit.
Exactly. If you finish, I think you are not done, but you can save it, I think. Save and hold, right?
Oh, no, sure. I have no idea about that. I actually generally.
Because I can see on several different dates people had uploaded something, and then finally the last version is what we see. Okay, or we can in fact see all the text variations there. So I don't know if there was a save option. So whatever was there previously, it's the same. I'm not going to change that setting. I'm only changing it to once you open the question paper, you will be given only 72 hours. Okay.
Sir, actually in assignments, actually it happens like that, but I'm not sure about exams, how they work. I mean,
No,
like,
even in exams, that's what I see. I mean, somebody's I can see. Okay, so something was saved on this day, something was saved on this day, and finally submission was complete on this day. That's what
okay.
I see. Okay, while evaluating. Yeah. So that will be there, but I don't know any. So just be careful, because if you just say submit, it might close your session. Okay, so that is something. So whatever was happening before, it will be, because I don't know much about these settings. I mean, the settings are fairly weird there. Okay, so I'll just keep the same setting as before, except 72 hours for answering. That's all. Okay. So in the last lecture, we were looking at the all pairs shortest path problem. In fact, towards the end, we were looking at dynamic programming formulation by Floyd and Warshall. Okay, so it's based on slightly, I would say, an interesting version of recurrence. Okay, so the only thing is they, for the recurrence or for the description of the path, they have introduced a new parameter. Okay, so pi uvr is defined to be the weight of a shortest path from u to v, but only thing is there is a restriction on the vertices being used as intermediary vertices. Okay, so you can only use vertices numbered from 1 to r. So if I take r as n, then pi uvn is the length of the shortest path from u to v, assuming that there is a shortest path. Okay, so if there is a path, okay, if there is no path, then it will be of course infinity. So the nice thing about this is it has a very simple recursive structure. Okay, so to begin with, if I set r as 0, that is, you are not, so assuming vertices are numbered from 1 to n, you are not allowed to use any intermediate vertex. So pi uv0 is essentially the weight of the edge from u to v, if it exists. Otherwise, it's of course infinity. Okay. Now pi uvr, so that is, you're basically looking at all paths that use only 1 to r as intermediary and the shortest among them. So weight of that is pi uvr. Now there are two possibilities for it. One is intermediary nodes are all from within 1 to r minus 1. Okay, so that is this possibility, blue colored line there. Or you are using r. So if you are using r, so until the point you use r, you're allowed to use only vertices numbered 1 to r minus 1. Similarly, after the use of r, remember that this is a simple path. So after the use of r, again you are allowed to use only intermediate vertices from 1 to r minus 1. Okay. So now the recurrence is as follows. So you take the minimum of the two. There are only two possibilities. Okay. So minimum of pi uv r minus 1, comma pi u to r, again using only 1 to r minus 1. Then again pi r to v, again using 1 to r minus 1. Okay. So just like how it works with the Dijkstra's or in general Ford's algorithm, this again is only exploring walks. Okay, so see, in this formulation, you will not be, when I say, okay, you can use 1 to r minus 1 and 1 to r minus 1, I'm not forcing that vertices cannot be reused. Okay, so this will be taken overall walks itself. Okay, so walks will also come into picture here. But of course, the minimizing one will be always a path provided there is no negative weight cycle. Okay, so assuming that there is no negative weight cycle, the one that minimizes the total weight will always be a path. Okay, because the moment you have cycle, and if it is not negative weight, you can just throw it off. Okay. Yeah, so this leads to a simple dynamic programming formulation. Okay, so you start with 0, so you initiate pi uv 0 and then keep on incrementing. So pi uv 1 is defined in terms of pi uv 0 for all uv. Okay, you might require, so what I mean is you first compute pi uv 0 for all uv, then for any fixed vertex, let's say u prime, so pi u prime v prime 1 is defined in terms of pi uv r for various vertices. So you might so here you require pi u r. Okay, that is pi u to 1 and pi 1 to v. Okay, so for higher r's, it's basically, so if you have pi uv r minus 1, it is enough to have. So that's a very natural dynamic programming formulation. Okay, so you can just have a table. So the only thing is the table will have 3 parameters, pi of u, v, r. So it has to store these 3 values. Okay, following the notation from Ericsson, so I've just taken this algorithm from Ericsson's book. We just denote it by distance. Okay, so Ericsson, what he does is he basically uses pi for representing the path. Okay, then distance for values. Okay, so I just defined pi as value itself here. Okay, so I could have defined it as path, then I will have to describe it slightly different. I cannot write this recurrence right away. But anyway, so at least this picture explains that part. Okay, so the algorithm, you initialize distance uv0 as the weight of the edge from u to v, and then from r1 to v, 1 to n, in fact, sorry, I should have corrected it. 1 to n, what you do is for every pair of vertices, you just update the distance uv r. Okay, so distance uv r will be equal to distance uv r minus 1 if this condition is met. Else it will be distance of u r comma r minus 1 plus distance of r comma v comma r minus 1. Okay. Yeah, so only deficiency that one would see in this algorithm is you will require a 3-dimensional array here. Okay, so you will require 3 parameters. Okay, so the graph has n vertices, then this array will have size n cube, n into n into n. Okay, or in fact n into n plus 1, because you also need 0 here. Okay, so that is one limitation. Implementation wise, you probably would like to have a 2-dimensional array, or if possible just 1-dimensional array. So this original algorithm is attributed to Kleene. Okay, so Kleene, and there are also a couple of other authors, but Ericsson just refers to Kleene. I'm sorry. The improvement is the following. So you can just see rewriting of the same algorithm. Okay, so what you do is you just use the 2-dimensional array. Okay, so again this yeah, so this has been like slightly generalized. I mean, no specific thing about indexing. Okay, so you just run over any vertex. So indexing is not really a matter as such, but yeah, this should be for r equal to 1 to n. Okay, so preferably that way. So yeah, so but the algorithm is slightly different now. Okay, so this is equivalent to for r equal to 1 to n, but it does not really follow that order, because we have really gotten rid of this 3rd parameter from the list. Okay, so what you do is you just update this distance value. You iteratively do the following: for every pair of vertices, you look at distance uv. Okay, and you look at this intermediary vertex. So r. So you see r as an intermediary vertex. So distance u to r plus distance r to v. If this value is smaller than distance uv, So you update, you repeatedly update this. Okay. Yeah, so this will take some time understanding. I will not go into the details of it. Okay, so if you understood this algorithm is also, I would say, among the algorithms that we have seen for shortest paths, this is the simplest one to understand. Okay, understand the correctness as well, because this recursive formulation immediately gives the correctness of the algorithm. There's nothing much to do. Only this implementation is bit non-trivial to understand. I'll just state it and leave it at it. Okay. So this is equivalent to this for r equal to 1 to n, but you suddenly gotten rid of uh, the third parameter. Okay. So but if you look at this carefully, so this is kind of justified here. Distance u to r comma r to v. Okay. So this is essentially what we do here, right? So distance u to r, distance r to v. So this r minus 1 was not really necessary, right? Because you at any iteration only that you are going to interested in. So at the rth iteration, you are interested in r minus 1. Okay. So and the interesting point is at every iteration you will be running through all vertices. So every entry is updated. Okay. So that means I can throw away r. So the entries for r minus 2, r minus 3, etc., etc. Okay, so this iteration, so I don't need this third dimension at all. That's essentially what this does. Okay. So that's all about all pair shortest path. I'll not really run through example and so on. I'll also leave it to you to analyze the running time. It's fairly straightforward. There are 3 loops, n into n into n. That's it. Okay, so nothing more, nothing less. Yeah, so we haven't gone through all algorithms for shortest path, particularly single source shortest path. So if you see Erickson's book, there are also variants using DFS, BFS, and so on. We have skipped all that. And the interesting point is, so for example, all pair shortest path. I think single source shortest path, not much improvements or not much attempts on improvement. Okay, so this Floyd-Warshall algorithm, people have attempted at improving it. Okay, so this n cube complexity, can you improve? That was the question. There has been a lot of research on that direction. So for example, I think there is a randomized algorithm which kind of improves this. Okay, it pretty much does it in n square time, but that may not work on all graphs, so there are some constraints on it, but still it's fairly efficient for most of the graph. And there are also very recent research which basically says that, like, if you improve upon this, you would be doing some drastic things in a related area called complexity theory. Okay, so something unusual would happen there. So in other words, improving performance of this algorithm would mean something drastic, in the sense that it would be as hard as proving some conjecture in complexity theory or disproving some conjecture in complexity theory. Okay, so yeah, with that note, I'll wind up the shortest path theme. So I'll wait for a couple of minutes for questions.
Hello.
Yeah.
Sir, okay. The one thing I want to clarify, in the previous algorithm, the clean algorithm, we were assuming that we are using r minus of the vertices. Any
Yes.
r minus one vertices?
Yeah.
Or these are numbered vertices or any r minus one vertices?
See, numbered is convenient to use. Okay, so this definition itself, it is convenient to use. Say that, okay, vertices numbered from 1 to r minus 1 or 1 to r. Okay, but in a sense, right, it really does not matter which vertex, right? You just want to say some subset of vertices. So that's what this algorithm, this modification does. It's confusing at first sight, so it would have been nice if you had just written this way. Okay, but I just copied this from the textbook. So see, this basically says, when I say for all vertices, so say up to, say, ith iteration, if I had vertices, say v1 to some vi. Okay, so this basically represents distance from u to v using only intermediary vertices as v1 to vi from the subset v1 to vi. Okay.
Yeah, okay, because we have run from R, suppose we run from R is equal to 1 to some P. Before
Yeah,
that P, all have been used in computing this distance. Now we are using the Pth vertex. So that's why it's
exactly.
similar to the previous algorithm.
Yeah, yeah. So, but only thing is, it really that indexing does not matter. So that's why Jeff Erickson just got rid of this. You just said for all vertices.
Okay.
Okay. Yeah. Any other question? Okay. Okay, so if there are no further questions, we'll move to the penultimate topic for our course. Okay, so this is about flows. Okay, so after flows, I'll be spending 2 or 3 lectures on complexity theory, particularly hardness of algorithms and so on. Basically, the theory of NP completeness. Okay, so I would say that flows and shortest paths are kind of fundamental to algorithms, are the most important algorithmic problems. So in fact, flow more so in the sense that, in fact, using flows, you can also solve shortest paths in a subtle way though. And at least from the recorded history, since the 50s, importance of flow has been understood and people have studied. Okay, so this is an example I quoted from Erickson's book. I mean, in fact, he got it from, I think, some classified, declassified military sources. So yeah, so at least the statement is as follows, or the story is as follows. So a couple of researchers are army generals. So they were studying. I mean, see, there was already a rivalry between Russia, USSR, and USA. Okay, so they are studying railway network, which basically link Soviet Union to the so-called satellite countries in Eastern Europe. Okay, so they modeled it as a graph. Okay, so with 44 regions or 44 vertices, and that graph also had some number of edges. 105 is what is written here. Okay, so each edge represents a link between the region. Okay, now, so what they wanted to study is, okay, how much material they can ship from Russia to Europe or vice versa. Okay, so they given weight for each edge representing rate at which material could be shipped. Okay, so what it is, they figured out by trial and error. So they determined that what is the maximum amount of stuff that can be moved from Russia to Europe. Okay, so what is the maximum amount of whatever material? I mean, if they were interested in nuclear materials, I mean, what is the amount that can be moved? And also, they're also interested in how do you disrupt. So if you want to cripple USSR, so how to disrupt the network, and what is the cheapest way? Okay, so by removing links, in fact. Okay, so by what is the minimum amount or minimum number of links that you need to remove so that the network is completely disrupted. Okay, so this is a classical example of a flow problem. Okay, so in general, you are given a network. Okay, so with capacities, so these weights can be seen as capacities. Okay, so this network will be a directed graph. Of course, whenever we use the term network, it's always meant to be directed graphs. Okay, so what you want to have is, so you'll have source and destination. Okay, so in this case, there is no source and destination. I mean, there were like source was Russia and the destinations were all these Eastern European countries. Okay, so you'll be having a source and destination. So you want to calculate the flow. Okay, so you can imagine weight as a capacity of each edge of transmitting. It may be goods carrying capacity or anything else. Okay, you want to compute the maximum amount of flow that can maximum amount that can flow from S to T. Okay, and this dual object, so that is the minimum way of disrupting the network. Okay, that is minimum number of links that to be removed so that the network will be disrupted. So this is called cut. Okay, so these two objects, they go hand in hand. They are fairly dual objects, and as per Ericsson, this is the earliest recorded use of flows and network cuts. Okay, in a network. In fact, I don't know how. So, if this was academically published, I don't think this was academically published. But in the late 50s itself, I mean, there was huge study of flows. Okay, so there is in fact one textbook dedicated to network flows. In fact, there could be multiple. I think one book is Ahuja and Magnanti. So they have written flows and networks. Okay, it's a huge book, completely dedicated to network flows. Okay, and there is also a book by I think Shriver. On combinatorial optimization. That book also has a fair bit of space dedicated for flows and min cuts. Okay, so various algorithms for it and so on. So for our purpose, and we'll be for this course, we will be looking at formulation of network flow. What is the problem? In fact, we'll be interested in maximization of the flow, and we'll see its relation to min cut. So the statement is called max flow min cut theorem. So there is a close relation. So weight of a minimum cut is equal to maximum flow amount that can be transported from the source to destination, and that naturally gives us an algorithm. And we'll see another algorithm due to Edmond and Carr. Okay, so that will be our objective. Okay, so the next this lecture and rest of this lecture and the next two lectures, we will be looking at flows and min cut. Okay.
Hello.
Yeah.
Sir, like, did not understand the flow part. I understood the min cut part. That is the minimum number of edges that could be removed to make the graph disconnected.
Yeah.
Min cut, right? But what is flow?
So flow is the amount that can be transported. I'll define it formally. Okay.
Okay, sir.
So basically, I mean, here they're saying the maximum amount of stuff that can be moved from Russia to Europe. That is source to destination. Okay. So that is a flow. So you can imagine that each edge has certain rate, right, or certain amount that it can carry. So at any point of time, what is the total amount that can be carried from the source to destination? That is roughly the flow. Okay, so we'll define it formally. Yeah, so this is again a picture from Jeff Erickson's book. This is how they had modeled the network. Okay, so these are nodes and these are links. Okay, so and each link has weight, saying its carrying capacity, how much weight or how much material it can carry. Okay, so now we'll start with the formal definition. So in the context of flows, I mean network flows or flows in general, we'll be having a directed graph. Okay, so here the term used is network. Okay, so this is called a network. So this has been traditional. Okay, so I'm in fact traditionally directed graphs are usually referred to as networks. Okay, basically owing to its use in operations research or even later on computer networks. So what we call weights, we'll call the weights as capacities. For our purpose, we'll just assume all capacities are non-negative. Okay. So for each edge, there is a weight we call as capacities. We are also given two distinct vertices, S for source, T for destination or terminal. Okay. An S to T flow for G is an assignment, let's call it as F, okay, to each edge of the network or graph, a non-negative number. Okay, so in most of the applications, these will be integers. Okay, we will not be dealing with real numbers. But the constraint is the following. Okay, so the constraint is the flow should be conserved at every vertex other than the source and destination. That is, if you look at any node, in the network or in the graph. Okay, so the net inflow, that is, you look at all incoming edges to a vertex u. Okay, you take sum of the values. Remember that there is an assignment, so f is assignment. So the assigned value should be equal to, if you look at all outgoing edges and take the sum of the outgoing values. Okay, so the net incoming flow should be equal to outgoing flow, or the total incoming flow at any vertex equal to the total outgoing flow at u. Okay, so we'll just see an example here. Okay, so this is an example again from the textbook. Okay, so here this is S and this is T. So these values are capacities. Okay, and these values are the flow assignment. Okay, so this basically says the capacity of this edge is 20, but I'm assigning a flow of 10. Capacity of this edge is 10, but I'm assigning a flow of 0. Capacity of this edge is 10, and we have assigned a flow of 10. Capacity of this edge is 15, but assigned flow is 0. Assigned flow is 0 here. Assigned flow is 5, assigned flow is 5, assigned flow is 5. Here assigned is 10 and capacity is 10 as well. Okay. Now let's just verify the condition of conservation of flow. Okay, so just let's go back to it again. So this conservation should be applied to all intermediary vertices, as we call it. Okay, apart from S and T, the source and destination. So source ideally should have outgoing flow, destination should have incoming flow. Okay, so that should not be, I mean, there could be outgoing flow out of it, but there should be a net surplus there, as well as for source there should be net deficiency. Okay, so basically you can imagine this network is used to transport material from a source to destination. Okay, so these can be roads, or these can be channels, or this, you can also imagine this as a pipeline structure. Okay, so there is a source and destination. There is a network of pipes. You want to estimate, so if I pump in some amount of fluid, what is maximum amount I can pump in, so that I mean, maximum amount I can pump from this source to destination through this network. Okay, so the only thing is the intermediary, they will not be taking out any liquid or whatever, say water network. Okay, so these are basically nodal points, maybe some connections and so on, but you won't be taking anything out. So that is conservation. That is, whatever is incoming should go out of it. Okay, so let's look at the conservation property for this network. So at this vertex, the incoming flow is 10. There's only one edge here. Okay, so you're taking sum of f value for all incoming edges. Okay, so there's only one incoming edge, so the net income is 10. Now let's look at outgoing. This has 0 outflow and this has 10. So the net outflow is 10. So 10 equal to 10. Okay, so you can verify that for all other vertices it's the same. So incoming flow here is 0 plus 10. Okay, this is again 0. So 0 plus 10 plus 0. Outgoing is only this edge and it is 10. Similarly, incoming is 10 here. There's only one edge. Outgoing is 5 plus 5, 10. So similarly, incoming is 0 plus 5, 5. Outgoing is 5. Okay, and this has net outgoing flow, that is 10, and this has net incoming flow, that is 10. Okay, so any flow assignment should satisfy this conservation property. Okay, now you can ask, so I didn't really talk about capacity, so what is capacity doing there? So any flow assignment such a way that for every edge the assigned value is within the capacity, we call that as a feasible flow assignment. Okay, a feasible flow, so a flow assignment is called a feasible flow. So this should be a flow. Okay, a flow assignment is said to be a feasible flow if for every edge the capacity constraints are met. That is, the flow assigned flow value is at most the capacity of that link or edge. Okay, yeah, so any question with respect to the definition?
Hello.
Yeah.
Sir, you were saying something regarding the S and T parts, that there should be a net outflow at S and net inflow at T.
No, there
That
will
is,
be. I mean that. Yeah, yeah.
can you explain more about that?
Yeah, so what we are saying is we are not insisting on the conservation property for S and T, right?
Yes.
So in effect, there will be an outflow from S, inflow from T into T. Okay, so that is what we are interested in. What is the net outflow out of S and inflow? So, but see, we didn't really say that S should not have any incoming edge or T should not have an outgoing edge. Okay, so it could be that you have an assignment, so there could be some outgoing edge this way, incoming edge to this, outgoing edge out of this. Okay, so you could assign some values here. So it can happen that there is no net outgoing flow from S or no net incoming flow for S. But those things we will not be kind of interested in. So what we will be interested in is there should be some amount which is gone out, and this, in fact, by conservation it will also happen that there is the same amount comes into T, and we want to kind of maximize that. Okay. So we are not insisting on conservation properties for S and T. See, if you also insist on conservation property on S and T, there's no effect in the network, right? So there is no see, the purpose of flow is like transport something. I mean, to estimate the amount that can be transported. So when you say transport, the source should lose some value, destination should gain some value, right?
Okay, okay.
Okay, so but here we don't insist any of that. We just say that okay, at S and T, we don't really care what happens. But intuitively, S should be losing something, T should be gaining something. That we didn't specify as such. We didn't specify that as such. But when we formulate it, it will happen so automatically. Okay. So yeah, we'll formulate the problem formally. So far, we have just defined what is a flow assignment, what are the conditions. So just for a flow assignment, all we need is conservation of flow, except at the source and terminal. And for a feasible flow, it should meet the capacity constraints. That is, at every edge, the flow assigned flow should be within the capacity. It can meet the capacity. So in this case, for example, it's equal to the capacity here. Whereas here, it's not even close to the capacity because you are not using this edge at all. Okay.
So the trick here is to find a suitable F. Are you saying that?
Yeah, so I'll put what optimization that we want to do.
Okay, sir.
Yeah, there is an optimization question here that we haven't posted. So we haven't posted any computational problem. We have just defined what is a flow. That's all. Yeah. So I mean, what I was saying is, so if you put this constraint to S and T, then this flow assignment does not really make sense. Okay, so gets interesting only when you have a source and destination, and you say that okay, for source and destination, I don't put the conservation constraint. I put conservation constraint only at other vertices. Okay. So in general, there could be multiple sources and destinations. Usually in the literature, I mean, we study only single source, single destination, because multiple source, multiple destination, you can easily convert this into a single source, single destination. Okay, that's not at all difficult. Okay. So now we'll have some couple of more definitions. Okay. So suppose F is a feasible S-tip flow. Okay. So we define value of this flow denoted by whatever. So F written within vertical lines is the total outgoing flow at S minus total incoming flow at S. Okay, so you look at all outgoing edges from S, take their flow, add them up, and then subtract the sum of all incoming flows. You look at all incoming edges to S and subtract that. Okay, so for that example that we had here, so there was no incoming edge at all for S. Okay, so outgoing edges contribute 10 here and 0. So this will be 10 minus 0 will be the value of this flow. So value of this flow here is, you just look at the source node, you look at the net outgoing flow. Okay, so here the outgoing flow is 10, but incoming flow in this network is 0. So hence the value of flow will be 10. So that's what is written here. Okay, so is the definition of value clear? You just look at the source node, you don't really look at anywhere else. So for defining the value of flow, you just look at source node. So how much you are able to send out, and also deduct whatever is incoming. Okay, so this does not assume that S should not have any income edges. There will be incoming edges. What you do is, whatever is coming in, you deduct it. So if you discount whatever is coming in, so what remains is the net outflow of S or source node. So that is defined as the value of the flow.
So regarding the conservation, I have a question.
Regarding what?
Regarding the conservation of flow
Yeah,
at
conservation. Yeah. Go ahead. Yeah.
any node. So we are saying that at source node and destination nodes, we are not concerned with the conservation of flow. But
Yes.
it can be said, because the source node is like pumping the flow, and the destination node is like receiving all the flow, right? But
Yes.
when we look at the graph or the network globally, the conservation must be preserved, right? Whatever has been sent from S must be received at T. So in that sense,
Sorry, I missed the last part.
I was saying that when we look at the complete network globally, locally we can say that S and T, the conservation is not conserved, because S is sending some quantity and is not receiving. We are ideally assuming that there is no incoming edge at S, and still it is sending something. So in that sense, the conservation is not.
No. So that's the point, right? So we are not saying that S should not have any incoming edge, even locally. Okay.
Okay.
So that is why I consider this quantity here. See, there is no restriction of no incoming edge. So when I say source is some designated node. It will also have incoming edges. So that is why I'm deducting this value. Whatever is coming in, I'm deducting. So this value of flow is the net outflow. Okay. So that is outflow minus inflow.
Okay, but this must be conserved globally, right? When we are considering S and T in the picture, whatever has been sent from S must be to, net outflow must be equal to the net inflow, right? At T.
Yeah, see, you can just imagine this network itself is a global network. Okay, so it's not a subgraph of anything. Okay, so only thing is the designated nodes is your choice. Now what you're saying is, except at the source and destination, the conservation property should hold. Yeah, so then what you said is right. Whatever is going out of S, the net outflow of S should be equal to the net inflow of T. So that is what this observation states. Okay. So what you said is, I mean, you don't need that global, local thing. Okay, so you can just imagine the whole network is global. Since we didn't insist on the condition that conservation property should hold at S as well as conservation property should hold at T, so the net outflow from S should be equal to net inflow at T. See, this could also be a negative value. Okay, so we are not saying this will be a positive value. It could be that net incoming flow is larger at S. Then net outgoing flow will be larger at T. Yeah, so this is, remember, we are not putting any modular sign here. I mean, we are not taking absolute value here. This could be negative. So we don't really insist that this is positive right now. I mean, when we talk about maximization, of course, it better be positive. So that implicitly enforces the condition that source node is something should be sending values and or sending material, and destination should be one receiving. But in principle, this definition does not insist on this to be negative or positive, I mean non-negative or whatever. Yeah, but what you said is right. Because of conservation, whatever net going out of S should be coming into T. So that's exactly this statement means. Yeah?
Yes, I got your point.
Yeah.
Sir, I have another question.
Yeah.
You were saying something that we don't study this problem for all the source to target pairs. But we studied the same problem for like all pairs shortest path. So is that because here we won't be able to reduce the complexity from whatever we get by applying this for all the pairs?
No, see, the point is I didn't really draw it and show. Okay, so if you have multiple sources and multiple destinations, right, it's fairly easy to convert this into a single source, single destination always. Okay, so maybe I can just do it immediately. Okay, maybe here. So suppose you have a graph where you have multiple sources. Okay, so these are the sources and these are the destinations. There's some graph here. Okay, so you can always convert this into a single source by adding a new vertex. Similarly, you can convert this into a single destination by adding capacities accordingly. Okay, so you can always modify the network. So that's the reason why they just study, and it simplifies a lot and makes things very easy to understand. But this is also without loss of generality. Okay, so if you look at Ahuja Magneti, they'll do this immediately. Okay, this is one shot thing. So you don't lose anything. You can modify the network so that there is a single source and single destination. Okay, so it's not exactly like all pair shortest paths and so on. The flow is slightly different. Okay, so you can have multiple sources and multiple destinations, but the only thing is it makes sense only when source and destination will be disjoint. The same vertex as source as well as destination won't really make sense here. Okay, so that is
okay, sir.
yeah. Okay, so yeah, so this again the same flow assignment. The value of the flow is 10. Okay, so the net outgoing value is 10 here, and the net incoming value is 10 here. You can just say 5 plus 5, 10, 10 plus 10 plus 0, 10. Okay, so yeah. Okay. So this is just again a definition. Maybe I'll just talk about the max flow problem. Okay, so let's talk about max flow problem and then I'll come back to definitions. Okay, so the max flow problem is the following. You are given a flow network, in fact directed graph, but in many books and many contexts it will be just called a flow network. Okay, so with capacity constraints. Okay, a feasible, so what the objective is to output a feasible flow such that the value of the flow is the maximum. Okay, so now our objective is to maximize the value of flow. Okay, so if graph, yeah, a feasible S to T flow. Okay, sorry, I just missed this, and S and T, source and destination. Yeah, so you are given a source and destination. Your objective is to output a flow such that the value is the maximum. Okay, so most of the times the context it will be clear. I mean, source and destination. So we will not really use S and T always. Okay, but S and T are given to us. So there is a source and there is a destination. What we want is a feasible flow where the value is the maximum. So that's what I was saying. So even if we didn't insist on this being non-negative, but the moment we say maximize this better be non-negative, right? This value be better be negative. So it's basically enforcing that S behaves like source. Okay, and similarly by duality, this ensures that T behaves like a destination. Okay, so the objective of max flow problem or network flow problem is to compute a flow assignment for a given network such that the value is maximized. Okay. Yeah, so with the definition, I'll stop here for today. So in the next lecture, so what we are going to see is we'll also define min cut or cut for a graph, for a directed graph. We'll see that the value of max flow is kind of equal to the value of min cut. So it's called max flow min cut theorem. And the proof of the theorem immediately gives us an algorithm for computing max flow. This is called the Ford-Fulkerson algorithm. And in the next lecture, we'll see an improved algorithm by Edmond and Carr, okay, which is what is used in the literature. It's one of the fundamental algorithms. The surprising thing is the flow problem immediately solves matching. Okay, so that application also we'll discuss on Monday. Okay, so if you I don't know how many of you have come across matching problems. So given a graph, you want to compute a perfect matching or a maximum weight matching. And so on. There are several variants of matchings. Okay, so all of these they immediately get solved using flow problem. Okay, so that's one of the interesting properties of flows. So, and that's one of the reasons why flows have become fundamental objects in combinatorial optimization or even operations research. So in the next lecture, we'll do a bit of mathematics over these flows. I mean, we'll prove some properties. So these definitions and all I'll go over. So there's, yeah, not much, but yeah, it's interesting. Okay. I'll stop here now. So just a reminder about the quiz. So those who joined late, so within next 10 minutes, I should be sending this as an email as well. Okay. So yeah, only difference is once you open the question paper, it's only 72 hours that you have. Okay, so that is something that should keep in mind. Okay, Srinivasa, can you stop the recording?